I'm delighted to be joined by Matt, Samar, Bailey, and Charlotte. Matt, our co-founder and CEO, holds an MSc in computation from the University of Oxford and a PhD in theoretical physics from the University of Cambridge. Samar earned her PhD in computational toxicology from University of Cambridge and joined Optibrium in 2019. Bailey holds a PhD in molecular biology and crystallography from Newcastle University and joined us in 2018 after working at Imperial College London. Charlotte is a scientist in our research division with an MChem in chemistry with mathematics. Together, Samar, Bailey, and Charlotte work on Sorella projects with customers. They apply AI and machine learning to drug discovery workflows, helping users to review hidden insights into the best compounds and the most valuable experiments. With that, I'll hand over to Matt to get things underway.
Thank you very much, Sophia, for your kind introduction, and I'd like to welcome everyone from the audience today. We've got a really interesting series of examples to present today. Really what we're going to be looking at is how a predictive model should identify when its predictions are reliable. Ideally, it should actually accurately estimate the confidence in each prediction. And of course, when the model is confident, it should also be accurate. So the model should know when you can rely on the predictions that it's making. But what we're going to see today, as we go through the examples, is how this information about the uncertainty in each prediction can actually add an enormous amount of additional information over the predictions themselves, helping us to make better decisions to identify high-quality compounds for our projects. And of course, if we prioritize our compounds better, that can save us an enormous amount of time and money by avoiding wasted synthesis and testing and quickly getting to the optimal compounds for our project's objectives. Before we get into the applications of uncertainty estimates, I thought I'd just spend a couple of minutes talking about how we can actually quantify the uncertainties in the predictions from our models. There are many different ways, and I've just summarized a few of the common ones here. The first is by far the simplest, which is simply associating a domain of applicability with our model. This enables us to assess the similarity of a new compound in the training set and identify whether it's inside or outside of that training set, i.e. whether the model is interpolating or extrapolating. And of course, we would expect a model that when it's interpolating to have higher confidence and lower uncertainty in those predictions than when it's extrapolating. But many methods can be more sophisticated and estimate the uncertainty in each individual prediction. Some methods, such as Gaussian processes, inherently estimate the uncertainty. On the right-hand side, you can see an example of a Gaussian process trained on a very simple sort of sine function. And what I can show here is the regions in green where training data was provided to that model. What you can see then is in the gap between the training data here, the uncertainties in the predictions become significantly larger. And of course, as we extrapolate beyond the boundaries of that training data, again, the model recognizes that and the uncertainties get higher. In the case of Gaussian processes, it estimates this as the posterior distribution for each individual prediction. Another popular method is conformal prediction. This can actually be applied to any sort of black box modeling method to estimate the uncertainties in each prediction. The downside of this is that it's a post hoc analysis and requires a calibration set in order to be able to quantify those uncertainties. So we need a separate set of data in addition to the training and test sets. And then finally, we can often use ensembles of models and look at the distribution of predictions from that ensemble in order to estimate the uncertainty in each individual predicted value. And in the examples you're going to see today, we've actually used the Alchemite deep learning imputation method that underlies our Sorella platform. And the way that this works is it estimates the probability distribution for each individual prediction using an ensemble of approximately 100 individual models generated using bootstrapped samples of the training data. This generates a probability distribution, illustrated here on the right-hand side in this sort of purple histogram. And we can take our predicted value as the mean of that distribution and the standard deviation of that distribution as a measure of its uncertainty. Now, I should note that the distribution doesn't have to be a normal distribution, and in fact, you can retrieve the full distribution of predicted values for each values for each individual prediction as well. But the standard deviation is a reasonable estimate of that level of uncertainty. And in many publications and presentations, some of which you'll see at the top of the slide here, we confirmed a very strong correlation between the estimate of the uncertainty from the model and the observed accuracies on independent test sets. And you'll see some examples of those coming up in just a moment. Now, of course, when we're making estimates of uncertainty, we also want to assess the quality of those estimates. Now, we might think that we can simply look at a correlation between the estimate of uncertainty and the error in each individual prediction. But actually, it's a little bit more complicated than that, because it's perfectly reasonable for an uncertain prediction to be accurate. But of course, what we shouldn't see is a confident prediction being inaccurate. So we don't actually expect a sort of a very strong correlation between the uncertainty estimates of individual predictions and their accuracies. We can see an example of this on the right-hand side here, where we've got absolute error in prediction on the x-axis and the estimated uncertainty on the y-axis. It's perfectly reasonable to have points up here in the top left, but what we shouldn't see many points in the bottom right here, roughly 2 standard deviations in uncertainty. We'd expect 95% of predictions to lie within that, as we can see here. However, while we can't look at individual predictions, we do expect that confident predictions to be more accurate on average. So we can actually look at the average error in the prediction as we increase as the confidence increases. One way to do that is shown here on the right-hand side. This is what's called a rollback plot. And what we're showing you here on the right-hand side is 100% of the test set. And on the y-axis, we're showing the root mean square error here about 0.75 log units. But as we move from the right to the left, what we're going to focus on is the subset of predictions in the test set with the greatest confidence, the smallest error bars, essentially. And what we should see, as we do in this case, is as the confidence in our prediction that in that subset increases, the root mean square error decreases. In other words, the accuracy improves. And so what you can see here from this blue line is that the accuracy of the model increases as we focus on those most confident predictions. So this is a nice way to sort of visualize this relationship. One can go further and quantify the calibration by, for example, looking at the expected normal calibration error, assuming normality in those error distributions, and other approaches as well. But for today, what you'll see coming up is we're going to focus on these rollback plots as a nice way to look at the impact of uncertainty on our predictions. And with that introduction completed, I'm going to hand over to my colleague Samar, who's going to talk to us about some applications of uncertainty estimates in those model predictions. So over to you, Samar.
Thank you, Matt, for the introduction. So I'm going to speak about how to apply the uncertainty estimates in model predictions. So when we have a good performing model, we can expect to use the predictions generated from that model to identify the best compounds and use the prediction straight away. So here is an example of a property that is well distributed across ranges from 0 to 5. And when we build a model for that property, we see a strong correlation between the observed property and the predicted property. In fact, in this case, the coefficient of determination, the R-squared, is almost 0.9. So in this case, we can reliably use the model to identify the compounds with the desired ranges of property. But of course, this is not always the case. And many of the properties that we would like to model are skewed in nature. So let's see how we can leverage uncertainties when the data is skewed. So here is an example of an activity endpoint in PIC 50, and we can see that it's skewed towards the left side, where we have the inactive ranges, whereas the desired ranges are where we have activity, high activity. So when we build a model on this property or activity, what we would notice is an overall moderate performance on R squared of roughly around 0.5. We do see some correlation between the observed activity and the predicted activity. However, the model is more accurate in predicting ranges where it has seen more examples, so the inactive ranges, the lower values. And for the points that are outside the range, what we see is the model is extrapolating in this region. And these points are associated with high uncertainty, which is the right thing. That the model is doing. So when the model is trying to make predictions for unseen range values, that will be associated with large estimated uncertainty. So let's see how that reflecting the rollback plots that Matt described earlier. So for the same property, the activity property, we see the observed versus predicted values in the right. And in the rollback plot, for 100% of the predictions, the overall RMSE is equivalent to 0.35. As we focus on the most confident predictions, removing those points with the high uncertainty, in this case, focusing on the most confident 50% of predictions, the associated RMSE drops. So we have an increased accuracy that is reflected in the right side with the points becoming closer to the identity line. And we can go further and focus on the top 10% of predictions. We see how the points become even closer to the identity line, and the RMSE drops to almost around less than 0.05. And so in this case, what this demonstrates is a strong correlation between the estimated uncertainty and the actual error. And so we can leverage where we are confident about predictions. In this case, the compounds with inactive ranges, we can reject them with confidence because they are not meeting the desired criteria. And later on, my colleague Bailey will explain how we can leverage this correlation to identify compounds that do meet the desired criteria. The second advantage or value of applying uncertainties is where the overall performance of the model is poor. So in this case, we have a model for an in vivo clearance in mouse where the R squared on the test set is 0.25. So in the first instance, we would assume that the model is not reliable and we cannot make any predictions out of it. But if we analyze the uncertainties, we still see a correlation between the estimated uncertainties and the actual error. So where we have a poor correlation for all the predictions for that property, which is associated with an RMC of 0.5, if we removed points with high uncertainty, focused on the most confident 50% of predictions, we start to see that the points become closer to the identity line, reflecting as a smaller error. So the error in this for 50% of predictions, 50% of the most confident predictions is 0.3. We can go even further, focusing on the most confident 10% of predictions, and we see that the error is even smaller. So what does this mean is even when the model is poor, we can still see a strong correlation between estimated uncertainty and the actual error, so we can leverage where the model is confident to make decisions. Uncertainties can also help us identifying unlikely experimental values. So we expect to see variability in experimental measurements, resulting either from artifacts or errors. And so we can use the uncertainty to identify measured values which are unlikely. So for example, here in the plot in the right, we can see that the distribution of predictions from a model is significantly different from the experimental value. And in fact, we can say it's more than twofold of standard deviation away. So we can reliably identify a potential false negative in this case, where we would like to either rerun the experiment or investigate the values further. So where the model where we can identify that significant difference, it highlights unlikely results, which are probably from experimental error, but it can also be from unexpected structure-activity relationships. In this way, we can also identify potential false negatives and rescue valuable compounds, or avoid false positive that leads to enormous waste in resources. So I'm going to just demonstrate detection of unlikely experiments using the same rollback plots that we were seeing earlier. So here there is a property of in vivo clearance in rat, where the model actually performed very well with an R-squared of 0.8 on the test set. So we see that strong correlation between the observed and predicted values. So for 100% of predictions, the RMSE is around 0.3. If we focus on the most confident predictions, we see that point become closer to identity line, the RMSE drops. And as we look at the most confident 10% of predictions, we see that point that is distant from the identity line. So the predicted value is significantly different than the measured value. And given the probability of the model generating accurate predictions overall, this suggests that the outlier might represent an experimental error. Another value that uncertainty can provide is prioritizing experimental resources. So we can imagine that in a setting of data drug discovery projects, we have multiple experiments and tested across many compounds. Some of these experiments are really important and informative to make decisions. And so we can prioritize our experimental resources where we can see that uncertainty is highest, which represent measurements that are most valuable to make. And so in this way, we can confidently progress the best compounds to the expensive downstream experiments and maximize the return on investments on experimental resources. And by that, I'm handing to my colleague Bailey, who's going to elaborate more on the value of uncertainties.
Thank you, Slor. I'm going to look at the value of uncertainty estimates for prioritizing compounds. There's a lot of information to be gained from having uncertainties for our predictions, and I illustrated that here on the right as an example, using having 4 predictions for 4 different compounds. The prediction is shown as the gray bar, with the bell curve around that being the uncertainty in that prediction. And then we have a desired range on the right, shown as this shaded region. And sometimes it's very clear whether the compound will meet that desired criteria, and whether the true value will be with desired range. For example, here in the top left, there's no probability of being within that desired range. In the bottom right, we have a prediction that is within that desired range, and that uncertainty is very small. And so we can say that there's a high probability that that true value lies within the desired range. In the other 2 cases, we have predictions that are close to the desired range. In this top right example, the uncertainty is quite small, and it doesn't span far into the desired range, so there's a very low probability.
that meeting the desired criteria. In the bottom left case, we have very wide distribution indicating a high uncertainty, which actually spans into that desired range. And that means that there is a chance that that compound will meet that desired criteria. And so in this example, if we had to choose between these two, the bottom left and top right, those two compounds, we would choose this one on the bottom left because that would have a greater chance of success. And so by having these uncertainty, that allows us to distinguish between these two compounds that have very similar predictions. So, and just as we want the predictions to be as accurate as possible, we do need these uncertainties to be as accurate as possible. So it's important to calibrate whether these uncertainties are likely to be overconfident or underconfident. And in some cases, they may show where more data needs to be collected in order to make a decision. For example, for this compound in the bottom left, with that high uncertainty, that one might be one that it would be determined to measure that experimentally because there is that high uncertainty and it's spanning from that desirable region to the non-desirable region. So let's take a look at this and in example and see how might the picture change when we're taking into account these uncertainties. So this is a hypothetical example where we're looking for a percent activity of the protein target, and we've made predictions for 10 compounds. And we can only choose 3 to move forward. Which ones should we select? We can reorder these compounds based on that predicted percent inhibition. And we can say that B, H, and S are the ones that have that highest predicted value, and those ones would be the ones we would like to move forward. However, if we knew the underlying uncertainties, which then would be the ones that we would progress? So looking at these uncertainties, we have a wide range of confidence in these predictions. We could see that B has a small uncertainty and it's likely to be around 80% inhibition. With compound H, that's much larger. It actually spans much higher and had the potential to be higher activity than B. In terms of that third compound to progress, S has a much smaller uncertainty than J. And depending on the target that we would set, maybe that the criteria would be, maybe if we said that was 70% activity that we would require, it's actually compound J that has higher likelihood of meeting that criteria than F. So let's now take a look at a real life example where we're using these uncertainties to help us prioritize compounds. So here we have an example using open source permeability data. Down here, I've got plots showing the experimental measurements against predictions made using our Sorella platform. And in this case, we can see that the experimental data isn't matching so well with the predictions. We don't have those values matching up very well. In particular, with these measurements at that upper end, where we have much fewer examples. So here we have 2 examples within the test set, which shows that we have that sparser data at this range. And what we can see is that we have high uncertainties for these compounds. And so that is showing that the model is recognizing when it's extrapolating to those ranges of data that's seen less often. And it's appropriately assigning a high uncertainty to these predictions. And as Samar talked about, we see these correlations between the estimated uncertainty and the accuracy to those observations, we can take a look for that. In this case, we can look at test set predictions with less than twofold uncertainty, what's shown here on the right, those most confident predictions. And in this case, those are highly accurate. We can see that the predictions match up well to the experimental data. And in this case, those are all at the lower end. That's the undesirable, where we have too low permeability to be successful. And so in this case, we can actually reject those with confidence and save time and money by not measuring those low and predicted with high confidence compounds. So although the predictions aren't very accurate in terms of the raw values that the predictions have assigned, we can see that those uncertainties appear to be guiding us to a good prioritization. So let's take a look at how we might prioritize these compounds. So in this case, we want a permeability of greater than a value of 1. And so if we set that cutoff and then calculate the probability that the compounds would meet that desired criteria, we can then see those results here in this middle box. Here's our probability, and then this is the experimental measurements. We can see that compound that achieved that high experimental result of 14 actually came out with the highest probability. And we see that many of these most probable compounds meeting that desirable criteria, you have the value of experimental value of greater than 1. And then if we look at the top 10 compounds with the highest probability of meeting the criteria, we get very different distributions out in terms of that experimental data. So what this is showing is that these probabilities accurately identify those best compounds. So this is an example of just looking at one single property and investigating that probability of success. But within drug discovery, the objective is to identify compounds with lots of different properties. And so here we're, in the case of drug discovery, we're balancing properties like potency, safety, and many drug-like properties to identify the best candidate. And so I'm representing that here in multi-parameter or multi-dimensional chemical space. And the region over where these parameters all overlap, that's where we find our drug candidate. But of course, there are cases where no good drug will exist, cases where we don't have properties that overlap and have all the required properties be required to bring a drug to market. And in these cases, the industry mantra is to fail fast and fail cheap. But in order to fail fast, what we would need to do is rely heavily on getting this information from predictions. And so in those cases of negative predictions, those actually can be just as valuable as positive ones. They lead to a reduction in wasted time and experimental resources. They might provide learning opportunities, which lead to rational redesign. So if we know early on that a particular set of compounds have a liability, then we can redesign the molecules to get around that liability. And then these things would ultimately speed up that discovery and development cycle, as it would keep the focus of the pipeline on those viable candidate compounds. And of course, I'm focusing on negative predictions, but positive predictions can also speed up that discovery and development cycle, as we are focusing that pipeline on the molecules that are most likely to succeed. And so always looking at that, getting that objective assessment of which compounds are most likely to succeed. But in order to make these kinds of decisions of failed compounds and which compounds to prioritize, we need to be confident that it is the correct outcome. And so that's really where the uncertainties come into this. Uncertainties in those predictions allow us to know whether we can be confident in those predictions. And one way of doing this is through the use of Stardrop's probabilistic scoring tool. So this is Stardrop's method for multi-parameter optimization. And what this does is it allows you to define all of the criteria that is required for a project to be successful. You can define the properties, the range of values, as well as an importance, which relates to how crucial that property is for the compound's chance of success ultimately. Very importantly, it takes into account the uncertainty in all of the measured or predicted data, and it provides an objective assessment of the compound's chance of success. And it gives a score for the likelihood of success, as well as a histogram, which relates each property has a separate bar of this histogram, and where the bars are highest, that means that the compound has met that criteria for the property, and it has done that with confidence. So for the scores that it outputs, those are on a scale of 0 to 1, 1 being that it has met all of that desired criteria. And we can visualize these scores within a snake plot in Stardrop, where we're going from the best scoring compounds on the left to the worst. And these have whiskers on the plot, these error bars which show the confidence in the overall score. And in this example, on this slide, we have these top 5 best scoring compounds actually have very much overlapping error bars. And so we couldn't say between these 5 which is our top compound. That's what this is showing. And then in this case, we could reject the bottom 50% with confidence. We can see that those error bars don't overlap with those of the top scoring compounds. And so they are very unlikely to be our top compound. And so with that permeability example, we were looking at the probability of for just one property. What this is doing is it's taking into account all of the properties and the criteria and giving you an overall score, and including that uncertainty as well. And if you'd like to learn more about probabilistic scoring in Stardrop, we have a recent webinar on our website, and this URL at the bottom takes you there. And so with that, I will pass over to my colleague Charlotte, who will talk about probabilistic scoring in practice in real-world examples.
Thanks, Betty. So I'm going to talk us through a couple of real-world examples where we've combined model statistics, the predictions and the uncertainties that Samar introduced us to earlier, and combine those into scoring profiles in Stardrop that Bertie's just described. We saw in previous examples how we can do this when we consider just a single property, but in our day-to-day projects, we often want to look at compounds that meet multiple criteria. So NPO profiles consider statistics for multiple properties, and we can calculate a single score for each compound based on the predicted values and the associated uncertainties, combining the probability of meeting each criterion and its importance. So in the NPO profile here, we've got multiple properties, and each property considers the statistics from the model. So we've got the phenotypic activity model with the predicted values and the uncertainties, and the desired range of values that we want to consider. We've also got the same for the stability model. And if you were to consider the model statistics for each of the properties here, it'd be very complex and challenging to do that manually. So the MPO feature in Stardrop considers all of the statistics from each of the properties and returns a single score. So we can rank the scores for each compound and find the compounds with the best score and use this for our decision making to prioritise compounds for screening. In this project, just over 6,000 compounds were tested in the phenotypic activity assay, and we applied the MPO profiles to the model predictions to score and rank the compounds, and we compared that with the experimental results. So here we've got the snake plot, where we've got compounds and their scores, and the highest ranking compounds are towards the left. And we've coloured the compounds based on their activity, so the active compounds in orange and the inactives in blue. And we can see that in the top 10% of all compounds, we have 85 out of the 86 actives ranked here. So we've found 98% of the actives with only 10% of the experimental effort. So we can think of that as an enrichment factor of 10. So we have one compound here that is measured active, but falls outside of the top 10% of the top scoring. So despite it being an active compound, it doesn't meet the criteria of some of the other properties. So when we had a look at the predictions for this, we saw that it was confidently predicted to have low stability. So we can reject this compound with confidence. We can also see that the inactive compounds in blue here have very small or no error bars associated with them. So we can reject these compounds with confidence and focus our experimental efforts on the compounds with the highest chance of success. So most of the active compounds that they all score highly, and they also have a good balance of properties, so meeting the ADME and PhysChem properties too. So these are high quality starting points for the project. So the next example also looks at ranking compounds using MPO, but this time looking at prioritising compounds for in vivo studies. So the goal of this project was to identify compounds with good in vivo efficacy, activity, selectivity, and log P. The project tested 150 compounds in vivo efficacy studies, and we modelled this data using an imputation model in Sorella, which we then used the statistics to prioritise the compounds for in vivo studies. In vivo efficacy is a complex and challenging property to predict, as many of the audience are aware of, influenced by many biological pathways and targets. So while the Sorella model showed promising correlation, you can see here in the plot on the right with the predicted and measured efficacy and an R-squared of almost 0.46. It's a promising model, and we wanted to confirm the value that this could add within an MPO scoring profile. So what we looked at here to investigate this was we built two different scoring profiles. The first one on the left excludes in vivo efficacy from the profile. So we've just got the primary target, the off-target, and log P in there. So we scored the 150 compounds and ranked based on score. So we've got the highest scoring to the left. And in the top 20 ranked compounds, 14 of them were efficacious as we can see here with the red and the blue, the red being the efficacious compounds. So in the top ranked 20 compounds, 70% of them are efficacious. We compare that to the plot on the right, and here we've included the in vivo efficacy in the scoring profile and scored and ranked compounds again. And if we look here in the top 20 ranked compounds, this time 16 are efficacious. So in the top ranked 20 compounds, 80% are efficacious. So we can see that adding the in vivo efficacy into the scoring profile helps us to distinguish between efficacious and non-efficacious compounds more accurately. So we can demonstrate what that means in terms of value to the project. And looking at the plot that included the in vivo efficacy in the profile, we can compare this prioritisation with what was tested in the project in practice. So of the 150 compounds that were tested, 39 of them showed desired efficacy, so 26%. And if we think about testing 20 compounds, we'd expect 26% of them to be efficacious, so 5 efficacious compounds. If we compare that with the selection based on the MPO prioritisation, we had 16 efficacious compounds in the top 20. So thinking of that as a threefold increase in the return on investment. So combining statistics from multiple models in the MPO profile helps us to prioritise compounds accurately and confidently, adding value to projects. We saw in the last example the enrichment factor of 10, and here a threefold increase in ROI. So with that, I'll hand back over to Matt for some conclusions.
Superb. Thank you very much, Charlotte, and Samar and Bailey as well. So just to wrap up with a few conclusions before we move on to the Q&A session, I hope what you've seen from today is that actually having reliable uncertainty estimates in each model prediction really dramatically improves the value of the model. It can help us to gain value from models that have poor overall validation statistics, where normally we would just have to throw the model away and not use it at all. But if we can identify within their predictions those that are most accurate, we can still use them with confidence to make good decisions. We can also identify experimental outliers where the measured value looks very unlikely based on all of the other data used to build that model. And again, as we've seen, it can also reveal high uncertainty regions that indicate novel, potentially high value chemical space where the model is extrapolating, particularly in the direction of those elusive good compounds that we're all looking for. And ultimately, this improves the decision-making in drug discovery. It can help us, as Charlotte has shown, to identify the best compounds for your project's objectives. It can rescue missed opportunities and avoid wasted effort by detecting these outliers and indicating perhaps retesting them before we miss an opportunity or we waste time and effort pursuing a compound based on faulty information. And again, Samar illustrated how we can prioritize the experiments that will add the most information, where the uncertainty is greatest. Getting that additional experimental data adds a lot of value. And we've seen this in the context of some real-world examples. These we're using our Stardrop and Sorella software. So just to tell you a little bit more about that, Stardrop is a very comprehensive platform for small molecule design, optimization, and data analysis. Guides decisions in terms of the selection of compounds based on the data we have already, but then moves seamlessly on to the design of the next round of compounds. And what we've been focusing on today is this probabilistic scoring approach for multi-parameter optimization that, as you've seen, helps you to very quickly target high-quality compounds for your project objectives. It can also help to explore all opportunities within a project chemical space and understand the structure-activity relationships in your existing compounds and data so that you can move seamlessly on to the design of the next round of compounds with a high chance of success through interactive design, and we call the glowing molecule. And this is backed up by a very broad range of the in silico modeling and design capabilities. And just for our audience today, I'd also like to point out that we are just announced, if you're looking in LinkedIn and other social media, our latest release of Stardrop version 8, which is going to bring some exciting new capabilities, particularly in the range of real-time collaboration within drug discovery. So if you'd like to see more, you can follow the QR code here, and we'd be happy to tell you more. We've also talked about our Sorella platform here, which is a proven and deployable AI platform that empowers drug discovery teams in ways that you've seen in the examples today. It helps to go from concept to candidate faster by using early stage data to more confidently predict late stage expensive outcomes. It can also help to identify better compounds. It can find those hidden opportunities caused by missing, uncertain, or incorrect data, and comprehensively explore optimization strategies for synthesis and testing. And it can inform the decisions that you're making in the context of your projects, helping you to choose the most valuable experiments to guide progression and improve return on investment, while understanding the relationships in your data to understand mechanisms of action and adverse outcome pathways. And I've really highlighted in blue here those particular capabilities that we've sort of focused on the underlying theory today. So with that in mind, I'm going to hand back to Sophia to introduce the Q&A session.
Thank you, Matt. Thank you all for such a thorough and well-considered presentation. As a reminder, if you have any questions, please add these to the Q&A panel at the bottom of the screen, and we will work through as many as we can with the time left. Any questions we don't have time to answer, we will try to follow up by email as soon as we can.
Thank you very much. So while Sophia's been introducing that, I can see we have a whole set of really fantastic questions coming in. So please feel free to add them, but we'll get through as many as we can in the next 10 minutes. So if I can start with the first one here. For many of the examples, there are large differences in the uncertainties. So what is making up those uncertainties? Because presumably the noise would be fairly similar for all molecules. So if I hand over maybe to Bailey for that one.
Right, yes. So yes, that's correct that the noise does make up, does contribute to the uncertainty, but there are many other factors that do also contribute towards that, such as the model uncertainty, also sometimes referred to as epistemic uncertainty, which is essentially what the knowledge that the model is lacking in terms of chemical space, as well as like biological space, as we heard about the ranges of data that it's seeing less often. So yeah, those kind of gaps in its knowledge. But we heard about Sorella uses an ensemble approach, and that actually takes into account all of those different factors and kind of combines them all, and so we're kind of representing all of those within that uncertainty, and then testing it against that independent test set as well.
Super. Thank you very much, Bailey. Now we have another one here. Are the rollback plots based on cross-validation tests, the cross-validation or independent or prospective test sets? So maybe Samar, could you answer that?
Yeah, sure. That's a great question. Yeah. So the rollback plots that we presented today are generated for an independent test set. So an 80-20 split between training and test. So we've taken the test set, the independent test set, and generated those plots.
Super. Thank you very much, Samar. So another one here is really great. What about activity cliffs, where a compound is structurally similar to other compounds but has a very different property? This can show up as a confident yet incorrect prediction when doing uncertainty quantification. How can we identify these and not be misled by the confidence in the prediction? Let's see. Maybe actually, Samar, you talked about activity cliffs, so maybe I could give that one to you as well.
Yep. Yeah, so we were describing that when we can identify some of the unlikely measured values. And so when the model is very confident about a prediction, but it's actually very different or significantly different from the measured value, there is a possibility that it's an experimental error, but it can also be an unexpected structure activity relationships, which is rightly described. So it can be an activity cliff. And so what we can do is take that compound and retest it or investigate the mode of action for that compound.
Absolutely right. Yes, of course, flagging that very uncertain relationship actually highlights the activity cliff, which is a very valuable thing to do as well. Here's another great one. Sorry, lots of questions. If your data set is very unbalanced, say 20-1 ratio between inactive and active, what happens if you build several models with more balanced levels, choosing various sets for the inactive set? Can the uncertainties help you build a most useful model, sampling the inactives? And any other considerations? I'll take that one because one of our colleagues actually did exactly that experiment and found it to be very useful. So what you can actually do is build multiple models, and instead of looking at an ensemble of all those models, you can actually look at the most confident prediction, and that turns out to be most accurate because those different samples of inactivity space will cover different chemical space. And so if you're giving it a new compound, it will find the model which it fits best within, and hence can give you the most confident prediction. So yeah, that's a really great idea. It is not an approach we've talked about today, but it is a perfectly valuable way to do that. This is a very simple one. Is probabilistic scoring in Stardrop available to all users? Yes, absolutely. It's part of the core features of Stardrop. So any Stardrop user can set up a profile and apply it to their experimental or predicted data, whichever you wish. Keeping an eye on the time. Yes. Okay. Here's a great one. How would you suggest we use the actual range of predicted values, including the mean and standard deviation? So the distribution, if you like. For example, in the case of the rat IV clearance, the confidence intervals stand almost the entire range of the measured values. I'm wondering how one would interpret the predicted values to inform decision-making in such cases. Well, I think, Bailey, you covered that very nicely in your part of the presentation, so maybe you could talk about looking at those distributions and how we use them.
Sure. Yes. Yes. Where you have those very high uncertainties. Essentially, the model is saying it's unsure of those values, but what we showed with in that example, we did have predictions that were very confident, and in fact, those ones did have high accuracy. So where we do have that correlation between the estimated uncertainties and the accuracy, we can pick out the confident predictions and use those to base our decisions. And then for the ones that are very, very large, then those ones might be the ones that we look to confirming those measurements experimentally. And we could use an active learning approach where we're feeding in that new measured data in order to improve the model overall.
Yeah, that's absolutely right. And I think the other thing is, even with quite a high degree of uncertainty, you can see in the examples that we presented today, I think some of Charlotte's as well, that you can actually still make remarkably good prioritization by looking at those probabilities of success. That uncertainty carries actually a huge amount of information. as well as the model predictions themselves. Okay, so here's another question. How do you determine the criteria to set within a scoring profile? So, maybe Charlotte, you could tackle that one.
Yes, so the criteria in scoring profile is looking for in the project. So the desired ranges. If we're wanting, say, activity less than a particular amount, we can set a function that will score the values against what we're looking for. So I think the answer really is it's up to you, and it depends on the project. Yeah.
Yeah, you're absolutely right. So every project is different. And of course, it's the project scientists that have the best perspective on what's required in terms of activity, physical, chemical, ADME properties, and so on. So it's completely flexible, and you can define it depending on the therapeutic indication, the route of administration, even properties of competitor compounds ahead or on the market. And we do also provide capabilities if you're not sure what the right criteria are to help you to determine them from historic data and test the robustness of your decisions to those criteria that you've set, so that you can be confident that you've got a good profile that will guide your project in the right direction. So absolutely. Well, I'm afraid I think we're about to run out of time, so I think I need to hand back to Sophia. We have a few more questions left, so we will absolutely follow up in writing with any questions that we haven't answered yet. But please let me just hand back to Sophia, who can wrap up our presentation for the day.
Thank you, Matt. That's all we have time for today. Any questions we don't have time to answer, we'll try to follow up via email as soon as we can. Details of our next webinar will be available on the Optibrium website and LinkedIn page shortly, along with other helpful news and information to help transform your discovery. All that's left for me to do is thank Matt, Samar, Bailey, and Charlotte for an insightful talk. Thank you all for coming, and we'll see you next time. Bye for now.